All right, thanks for the introduction. So hello and welcome from my side as well. I'm Raphael, PhD student at Johannes Kepler University in Linz, Austria. And yeah, I'm happy to present to you some of our results on playing with machine learning in a dynamic compiler. But let's first start with the background, the context, what we are working with, and this is loop vectorization. So what is loop vectorization? It is an optimization or transformation which turns the body of a loop into so-called vector operations, which then can execute multiple of these operations at once. So for example, we have this loop here doing some array additions, and if the hardware support for such uh, vectorized operations is available, then we can get rid of 3/4 of the number of loop iterations by having 4 of the loop bodies executed at once with those vectorized operations here. Typically in a compiler, there are multiple ways how to optimize a loop. So there is unrolling, tiling, peeling, vectorization. So often there have to be made trade-offs to what optimizations to prioritize. So for example, in the Graal compiler, unrolling is deemed less important than vectorization. So the typical unrolling of loops is omitted if a loop is vectorizable. And later on, after vectorization has been done, there is a special unrolling for vectorized loops. So for example, when having this loop in vectorized format, we could then unroll it with an unroll factor of 4 and would produce a result looking like this, for example. However, the interplay of unrolling and vectorization is often a bit hard to grasp. So making heuristics for finding the optimal unroll factor after vectorization can be kind of tricky. And this is also the case in the Graal compiler. So we did this little experiment testing on a lot of GraalVM's vectorization benchmarks. How is the performance for using an unroll factor of 8 versus an unroll factor of 1, so no unrolling, after loops have been vectorized? So the results look like this. So smaller than 1, we have all the benchmarks where we have a slowdown when vectorizing, when unrolling with an unroll factor of 8. And on the right-hand side, we have all the speedups. So no, clear results. So you cannot decide this statically, basically. The problem is that the engineers in the Graal team haven't found a suitable dynamic heuristic for doing this decision, what unroll factor to use after vectorization for each loop on its own as well. So we're kind of in a problem here. And based on previous research with machine learning, we just thought, can machine learning either do better in that case, or can machine learning help us in either finding problems, finding performance bugs, improving the existing heuristics in the Graal compiler for deciding what unroll factor to use after vectorizing loops? So what do we need to use machine learning in such a task? So there are several prerequisites which have to be met. Of course, when you're dealing with machine learning, you always need a lot of data. You need to automatically generate information on what loop unrolling factor to use for particular vectorized loops. You need to identify when to use what parameter in which context. And you need to then train a machine learning model with all that information so that you can use this model afterwards. So for the first task, for identifying what is the best unrolling parameter, we simply have to do performance measurements. It is not that trivial because we're in a dynamic compiler. Performance measurements isn't that easy, but we had a paper about this for solving these problems and getting consistent performance measurements. Essentially, what we are doing is for each vectorized loop, we create versions where we test all the different unroll factors and then store which of these unroll factors is the best one. And this is the label, so the optimal value, which we want to have the machine learning model to predict later on. We also need to describe each loop which we want to make a prediction on later on. So this is called feature extraction. We extract features describing our vectorized loop. I will talk about these features later on. Let's just leave it at that right now. And the tuples consisting of feature information and the label information is then used to train a machine learning model. This machine learning model can then be deployed, and after another vectorization phase, where you have then a loop and you want to decide what unroll factor you use. You just extract the program features for the loop, feed them into your machine learning model, and it will hopefully predict the best unroll factor to use for this loop. All right, what about the data generation phase? As already mentioned, this is based on a previous work we already did. Essentially, we had this assumption that vectorized loops are independent from each other, which will not hold in all of the cases, but in general, this heuristic works kind of well. Our approach, to put it simple, is we create different versions of our functions. We have one baseline version where we have all vectorized loops unrolled with an unroll factor of 1, so essentially not unrolled. And then we have one version for each loop and each corresponding unroll factor. So we can then compare the baseline with the corresponding version of the function and then determine which of the unroll factors is the most beneficial one for each of our vectorized loops. And with this setup, we only need 9 versions rather than 25 when spanning a grid over the state space of loops and all unroll factors. All right. With this approach, we created 140,000-ish data points, so vectorized loops, which we measured. These were collected from 231 micro benchmarks, which are used in the GraalVM for tuning and designing vectorization heuristics. 190 features, so the data essentially looks something like this. We have one data point, one vectorized loop in one row being consisting of a number of features describing this loop and also the value which we want to have our machine learning model to predict later on. We also did some data pre-processing, of course, because there can be data points like this one here where we have either a very little number of performance measurements, or the speedups for the different measured unroll factors are very close to each other. So it is really hard to identify that such data points are not noisy or produce noisy results. Therefore, we had to get rid of some of them. And by some of them, I mean about half of the whole data, just to be on the safe side. So much about the performance data we collected for having the data which we want to have our machine learning model to predict later on. What about the features we are using for describing our vectorized loops? So for this example, I will show some of the features we were using. In essence, we have 3 categories: the vector operation features, the vector component features, and the graph features. So for the vector operation features, this is basically just describing the outermost part of the vector operation, which is found here. So in this case, the outermost part, can't see much here. The outermost part would be a vectorized right. So we assigning something to an array. Then we also have information about the type of the vector, which in this case is a float 64. And from profiling, which is also used in the Graal compiler, we get information about the average number of loop iterations we have in our vectorized loop. As you can see, our features can be of different kinds. We have this classic numeric features like the iteration number. We have also categorical features like the vector kind, where the feature values are not comparable or ordered between each other. For the vector component features, we are then considering all the information which builds up the vector operation as a whole. So I mentioned that the outermost vector operation part is this vectorized right. But inside we have this math.max in this case. So we're doing something like a vectorized map operation. And there can be multiple components building the vector operation as a whole. So what we are doing here is we are creating a histogram where we count all the occurrences, including the types of the different components this vector operation as a whole consists of. And we also extract information about the number of nodes and edges of the vector operation. Nodes and edges because in the Graal compiler we are using a graph-based intermediate representation, and therefore we are aggregating some information about the subgraph of the vector operation. Vector groups are not shown here. They just aggregate different vector operations which are not related to each other. And the third component of features are the graph features. I already mentioned, the GraalIR is a graph-based intermediate representation, and to put our vector operations, our vectorized loops, into the context of the function as a whole, we also extract features about the surrounding function and its graph features like node and edge counts as well. So in total, we had about 190 different features we extract. However, for the histogram features, we did some feature reduction because we had a lot of features which are only present in very few data points. So we're not sure if the information taken from them can be used as such because they only represented in very few data points. So we removed a lot of histogram features, ended with about 142 features in the very end. So much about the data generation. We created a lot of data. We also took a look at this data and in terms of what is the distribution of labels, so of best unroll factors we found in the training data. You can see we have this slight tilt, which means that it is rather performant if using smaller unroll factors after vectorization. However, the data is, let's say, fairly balanced. However, we also took a look at this data when you're removing all the classes from the standard library, from the Java standard library. So just taking a look at the real core benchmark functions and not at the called functions from the standard library. And there, the distribution looks vastly different. We see this, we see that it is very likely that larger unroll factors produce faster results in that case. I mean, from our point of view, that this was kind of expectable. We explained it that the benchmark functions themselves are typically designed to have long-running loops in them to show off that different loop optimizations can bring much to the table. On the other side, the standard library functions are often or more likely to consist short-running loops, as they are therefore called more frequently. All right, so much about the data. For model training, we decided to use a random forest classifier, which uses multiple decision trees and the majority vote to get to an overall result. The main reason we used a decision tree-based model is that this thing is readable. So we also worked with deep learning in the past, but the model isn't really readable anymore. And in contrast, a random forest would look like this, for example. So we have a small snippet from a decision tree taken from our random forest. What you can see here is that for each node, which is a non-leaf node, we have the split conditions. So when a data point consisting of some features enters this tree at the root, then it takes a look at the split condition, and depending whether the condition is then true or false, the left or the right branch is followed. And then we have for each of our nodes the dominant class, and for the leaf nodes, the dominant class would mean that a data point, when following all the paths through the tree, would end up in this or that leaf node. The dominant class would be the predicted value, basically. And the lower the impurity in these leaf nodes, the better, because we could split the training data in a good way if the impurity is very low. All right, of course, we did not mix up training and test data when evaluating. This would be not good, so we came up with a cross-validation setup where we randomly splitted our data into batches of 10 benchmarks, and the remaining 222 benchmarks are then used to create a machine learning model, and one of the batches of 10 benchmarks is then used to test the model. So basically, we had 23 submodels, one to test each of these chunks of 10 benchmarks, and so we do not have an overlap of training and test data. All right, what training configurations were we interested in? What did we evaluate? So first of all, we trained different models based on either using the standard library data or not using the standard library data. We also investigated whether using the graph features describing the function as a whole are beneficial or not. And we did some tree pruning in our configurations. Some configurations with pruned trees and some without pruned trees. What is tree pruning? It is the process of cutting off the decision trees at some level to not learn all the noise and all the peculiarities of the training data. So in general, pruning the trees will allow the model to better generalize to new unseen data, because overfitting should be reduced in theory. All right, so what were the results? I've showed here some of the training results for the different configurations. The main diagonal shows the number of correctly predicted data points. The x-axis shows the predicted label, the y-axis the true label. So what can we see here? First of all, taking a look at the training results from training with the standard library data, we can see that the accuracy is okay, 40% when taking into account that we have 5 different unroll factors, which can be the prediction results. So they are often off by 1 errors, for example. So 40% is okay-ish. However, the accuracy significantly drops when we are omitting the graph features from training, which also makes kind of sense because we are losing information which seems to be valuable for the machine learning model. We also tested on the training data, just for the sake of having statistics here. We wouldn't do that actually. But as you can see, when using a large random forest without this tree pruning, the accuracy on the training data is kind of high because we have this overfitting. On the other side, when pruning the trees, the accuracy on the test data, on the unknown data, becomes better, which also makes sense because overfitting is reduced and the model better generalizes to new and unseen data. What was also interesting, though, is that, our prediction result is more likely to predict to use an unroll factor of 1. And this with a way higher percentage than even in our training data. So we have 35 to close to 50%, which the model would predict to use an unroll factor of 1 in contrast to the 25% in the training data. This we also found kind of interesting. All right, for training without the library data, the results are similar-ish. So the accuracy is obviously a bit higher, or definitely a bit higher, which makes sense as we are using way less data and we're not using the standard library data. So the benchmark data is more similar to each other, and therefore it is easier for the model to adapt to this data. And also the distribution of the prediction is more similar to the whole training data. All right, but I mean, accuracy and stuff is cool, but does it tell us anything about the performance when deploying this model in the compiler? I mean, good accuracy doesn't necessarily lead to good performance when deployed. Because you could have something like this, you have your machine learning model with an accuracy of 66%, for example, but when deploying this model in the compiler, you could have a slowdown on the one misprediction, on the one mispredicted function of 10%, and you get a slowdown as a whole. So accuracy alone is not sufficient to evaluate these models. So of course we implemented or used this model in the Graal compiler directly on these benchmarks using the same cross-validation setup. So again, a clear distinction between training and test data. What is shown here is the result for the benchmarks where we had either significant speedups or slowdowns. We had some 5 to 10 smaller slowdowns, but way more speedups in these benchmarks. We even removed, out of fairness, some of the benchmark results here where we had 4 to 6x speedup. This unveiled actually a bug in the Graal compiler in the vectorization phase, which we reported, and this bug is already fixed right now. What about the numbers? So for all of these benchmarks where we had either clear speedups or slowdowns, the geometric mean of the speedup is between 8 and 12% for the different models, so good speedups. What we also found is, pruning is always better, which was the assumption in the very beginning and was confirmed then. But what we also found is that we had some overheads in terms of overall compile time, and this strongly correlated with the size of the machine learning model. So we took a look at this in more detail and found that model loading is a very expensive task. So 60% of the overall compile time was spent in loading the machine learning model. I mean, this is more of a problem in these micro benchmarks we were using, and maybe not that big of a problem in real world programs, but it is nice to see. In contrast, the prediction itself, so using the machine learning model, is fairly cheap actually. So it is a primitive random forest decision tree based model, so deep learning could be a bit more expensive, but yeah, in that case, not really expensive. What is even more expensive is the time spent in collecting the features. So invoking the model only takes 18 to 20% of the time which is needed for invoking the model and extracting the features beforehand. So feature extraction is kind of expensive. And last but not least, we also evaluated our models on da capo and Scala da capo, which is completely new data, which is very different from those micro benchmarks. But still, we wanted to test how a model trained on just micro benchmark data will perform when trying to generalize on totally different data. The results are mediocre, I'd say. So we had some significant slowdowns in da capo and Scala da capo, one significant speed up in Scala da capo as well. But overall, as you can see, we have some slight regressions here. Compile time is okay, I'd say. So from this we can conclude that a model trained on just the micro benchmark data will not be sufficient to generalize on larger benchmarks or even real world programs. Yeah. All right. With this, I'm coming to an end. I have shown you how we try to improve vectorization heuristics in a dynamic compiler with machine learning. I told you about the problem that the unroll factor is kind of hard to identify after vectorization. Told you what we did to obtain the data, what we did in model training with our random forest, what configurations we evaluated, showed some results about the training and the performance evaluation when using this machine learning models in the Graal compiler. And with that, thank you, and I'm open for questions.
Thank you for your talk. That was very interesting. Have you considered using like synthetic data sets as well, or like generalizing from the benchmarks by like creating like procedurally generating like loop like vector like features to get hundreds of thousands of examples? And because it can be biased towards like you might not be choosing optimal loop unrolling factors in the it's like just repeating the same training.
I see what you mean. It could be the case that these micro benchmarks are biased, and we found that it seems that these micro benchmarks are kind of similar to each other. So we still had some overfitting in the whole process. It might be countered by creating this synthetic benchmarks. Actually, for this approach for data generation, we proposed some months ago. We actually tackled this problem by enabling automatic data generation of arbitrary data, so we wouldn't even need to create synthetic benchmarks. We could just use a bunch of user data or walk over GitHub and select programs. But we specifically wanted to work with this set of benchmarks as we directly wanted to compare with the data which is used for evaluating these heuristics and vectorization heuristics in the Graal compiler. But in general, it would make sense to create larger sets of benchmarks synthetically or by grabbing some GitHub programs, for example.
Hi. So in machine learning, people had looked into the model, into the weight of models like CNN transformer, and see what they are doing from a symbolic standpoint of view. Have you thought of doing the same thing for your work and try to see what the what the random forest is actually doing and try to get a simple heuristic out.
Yeah, I mean, I've showed a snippet from the random forest, and we also investigated the structure of our random forest, of our decision trees, and found some of the parameters which are deemed very important, some of the features which weren't considered to that extent in the current heuristic. So this was one reason why we're using this decision tree based structure, so that we can get information and improve upon the existing heuristics. Yeah, definitely.
Thank you. I wonder which microprocessor architecture you were evaluating on, and whether you'd expect to see any differences in terms of speedups over different architectures.
Yeah, I think there should definitely differences between different architectures. So we didn't consider it in this work, but in the past we have considered different architectures, and the optimizations which are beneficial and not make a huge difference depending on the architecture, especially when you're dealing with vectorization kind optimizations, because the vector size and all the underlying features are of a big importance. So this will definitely make a difference when run on different architectures. Yeah.
All right. Do we have a last question? Otherwise, let's thank the speaker.